So we continue the exercises. Okay, we'll now do two problems which illustrate once more the principle of divide and rule which I explained when proving the Weierstrass's theorem. So there are some integrals which we want to estimate. So it is a good idea to split sometimes the integral over a set and its complement. On one of the sets we know that the measure is small, we don't know too much about the function. On the other, we know that the function is small, but we do not know too much about the measure. So these two complementary things will compensate each other, and we will be able to control the integral and estimate it nicely. So this is the idea which we want to do. So here are the two exercises which I want to do. So 6. So excess mu, measure space, mu x equal to 1. G R to R bounded uniformly continuous function. Fn measurable functions. Fn converges to f in measure, f measurable. Show that integral over x g composed with fn d mu converges to integral over x g composed with f d mu as n tends to infinity. So what is g composed with f? At x is g of f of x. Okay, solution. So g is bounded, so we can say g less than or equal to m, and for every epsilon positive there exists a delta positive such that mod x minus y less than delta implies mod gx minus gy is less than epsilon. Okay, so now you take a, so given epsilon there is a delta, and we define a and delta to be set of all x in x such that mod fn x minus fx is greater or equal to delta. Okay, so then we know that fn converges to f in measure, so that will imply that mu of a and delta tends to 0 as n tends to infinity for every delta fixed. Okay, so now we are looking at integral over x g composed with f n d mu minus integral over x g composed with f d mu, and that is less than or equal to integral over x mod g composed with fn minus g composed with f d mu, and that we are now going to write as integral over a n delta mod g composed with fn minus g composed with f d mu plus integral a n delta complement of mod g composed with fn minus g composed with f d. So we have split the integral into two parts. So on a and delta we know that the measure goes to 0, but we don't know too much of it, but we know that g is a bounded continuous function. So integral over a and delta mod g composed with fn minus g composed with f d mu. Since g is bounded by m, this is less than 2 times m times measure of a and delta. And on the complement a and delta, complement mod G composed with Fn minus G composed with F d mu. Now what is this? Now if on An delta complement, what do you know? You have mod Fnx minus Fx is less than delta, and therefore G of Fnx minus G of Fx will be less than epsilon. So we have that, and therefore the G of Fn minus G of F is less than epsilon times mu of An delta complement. We don't know much about that, so that is less than mu of x, and that is epsilon. Okay, so now we are through, just as we did in the Weierstrass theorem. So given eta positive, choose epsilon such that epsilon is less than eta by 2. This fixes delta. Now choose capital N such that for all n greater or equal to capital N, mu of An delta is less than epsilon by 2. And therefore this implies for all n greater or equal to capital N, integral over x, G composed with Fn minus G composed with F you can put it inside d mu. The stronger result is less than epsilon eta, and hence the result. So that proves the theorem. Seven, xs mu measure space, mu x equal to 1. So let M be the collection of all equivalence classes of measurable functions with respect to equality almost everywhere. So you say F is equivalent to G if F equal to G almost everywhere, and the set of all equivalence classes F bar equals set of all so equivalence class okay. Let phi from 0 plus infinity to 0 1 be a strictly monotonically increasing function, continuous function, such that phi 0 is 0, and such that for all x y greater than or equal to 0, phi of x plus y is less than or equal to phi x plus phi y. So example, phi of x equals x by 1 plus x. Check. So this you can check. So I give you explicit example, but this we don't want to get bogged down by this example. So these are the essential properties which phi must have. Okay. So now A, define on M d of f bar g bar equals integral over x phi of mod f minus g d mu. A, d is well defined. Okay, because if you change the, it doesn't matter, since f and g, if f1 bar equals f2 bar, g1 bar equal to g2 bar, then f1 minus g1 is equivalent to f2 minus g2, and therefore so the phi of mod f1 minus g1 is equivalent to phi of mod f2 minus g2. That means they are equal almost everywhere, and therefore d of f bar f1 bar g1 bar is the same as d of f2 bar g2 bar. Okay, so it doesn't matter by which representative you calculate, and therefore this is well defined, and also phi is between 0 and 1, and therefore integral phi on x d mu is always less than plus 1. Okay, so it is well defined. So this is well defined. Okay. B. D defines a metric on M. So D is of course greater or equal to 0. D of f bar g bar is the same as d of g bar f bar. That's no problem. Now assume if f bar equal to g bar, that means f is equal to g, so mod f minus g equal to 0 almost everywhere. That means phi of mod f minus g equal to 0 almost everywhere. Therefore d of f bar g bar equal to 0. Conversely, if d of f bar g bar equal to 0, that means integral of phi of mod f minus g d mu over x equal to 0. This is a non-negative function. This means that phi of mod f minus g equal to 0 almost everywhere. But phi phi is strictly monotonic increasing, and phi 0 equal to 0. So this means mod f minus g equal to 0 almost everywhere, and that is f bar equal to g bar. Okay, so that is also true. Then the triangle inequality. So you have f bar minus g bar, or rather f minus g is less than or equal to f minus h plus h minus g, and therefore phi of mod f minus g is less than or equal to phi of mod f minus h plus mod h minus g. So here we use the other hypothesis, that's equal to phi of mod f minus h plus phi of mod h minus g, and therefore this implies that d f bar g bar is less than or equal to d of f bar h bar plus d of h bar g bar. So therefore d defines a metric. Okay, so now is the interesting part of this exercise, namely Fn bar in M. Okay, then Fn bar, and let's say f bar also in M, converges to f bar in MD, that is with respect to this metric, if and only if Fn converges to f in measure. It doesn't matter which representative we take, because we saw that if two functions differ almost everywhere, then they converge to the same function in measure, and so it doesn't matter. Okay, so the Fn converges to f in measure. So the convergence in measure can be thought of as a metric convergence in some suitable topology, in some function space. Okay, so this is a very interesting property. Okay, so let us assume that Fn bar converges to f bar in MD. That means integral over x mod phi n minus phi n of phi of mod Fn minus f d mu goes to 0. Now you take a and epsilon positive, okay, a and epsilon equals set of all x in x such that mod f n x minus fx is greater or equal to epsilon. So integral over a and epsilon mod phi of mod fn minus f, everything is non-negative, d mu is less than or equal to integral over x phi of mod fn minus f d mu, and this is greater, where phi fn minus f is greater or equal to epsilon, phi is monotonically increasing, so fn minus f greater or equal to epsilon, phi is monotonically increasing, therefore phi of mod fn minus f is greater or equal to phi of epsilon. So this is greater or equal to phi of epsilon times measure of a n epsilon, and epsilon is strictly positive, so this is strictly positive, and therefore you have mu of a n epsilon is less than or equal to 1 by phi of epsilon, which is strictly positive, and integral over x mod phi of mod fn minus f d mu, and we are told that that goes to 0, and therefore you have that fn converges to f in measure. Now conversely, let fn converge to f in measure, okay, to show fn bar converges to f bar in MD. Okay, so phi is continuous. So given any epsilon positive, there exists a delta positive such that mod x less than delta implies mod phi of x is less than epsilon. Okay, so because it's continuous at 0, so and phi of 0 is 0, and therefore we are using continuity at 0. Okay, so now let us take integral over x phi of mod fn minus f d mu. So again we are now going to use the epsilon delta, I mean the divide and rule. So this is equal to integral a and delta phi of mod fn minus f d mu plus integral a and delta complement phi of mod fn minus f d mu. Okay, so the first one, phi integral a and delta phi of mod fn minus f d mu. Phi is between 0 and 1, so this is just less than mu of a and delta. Now what about the complement? Integral a n delta complement phi of mod fn minus f d mu. So on a n delta complement we have mod fn x minus fx is less than delta. So that means phi of mod fn minus f is less than epsilon. So phi of mod fn minus f is less than epsilon. So this is less than epsilon times mu of a n delta complement. We don't know anything about it. This is less than mu of x, that's equal to epsilon. Okay, so given eta positive, choose epsilon such that epsilon is less than eta by 2. This fixes delta Now choose n such that for all n greater or equal to capital N, you have mu of a n delta is less than eta by 2. Okay, and that will tell you that d of fn bar f, which is equal to integral over x mod phi of mod fn minus f d mu, is then less than eta for all n greater to n, and that is exactly saying that is fn bar converges to f bar in m. Okay, so with that we complete the exercises, and next time we will start on a new topic.